Hey everyone, and welcome to today's Explainer. Today, we're diving straight into the mechanics of arguably the most transformative tech of our lifetime. The sheer pace of AI's evolution is just staggering, right? We've gone from simple parlor tricks to systems that can see, hear, and literally generate reality in just a few short years. So let's peel back the curtain and demystify how all this actually works.
Just to put things into perspective, let's look at the last decade. 10 years ago, state-of-the-art AI was struggling just to spit out a blurry, grayscale face. Fast forward to 2020, and sure, researchers were making highly realistic deepfakes, but it was incredibly costly. We're talking 50 hours of data and $15,000 in compute just to generate a 2-minute, totally static script. But today, we've got instant dynamic voice cloning that can converse with you in real time. So how on earth did we jump from rigid and wildly expensive to instantaneous and totally dynamic?
Well, here's our roadmap to figure that out. We'll start with the unstructured data problem, break down the anatomy of a single neuron, build a deep network, figure out how machines actually learn, and finally, look at how to avoid the overfitting trap.
All right, part 1, the unstructured data problem.
So, to really understand deep learning, we've got to look back at the biggest roadblock early AI faced. The original pioneers thought, hey, we'll just ask an expert how they make a decision, write down a bunch of if-then rules, and boom, the computer does the same. But they hit a massive wall called Polanyi's paradox. It basically states, we know more than we can tell. Think about it. If I show you a picture, you instantly know if it's a dog or a cat, right? But if I ask you to write down the exact mathematical rules for how you know, you can't. There are just infinite edge cases. Manually writing rules completely falls apart for complex, real-world tasks.
Traditional machine learning, it loves structured data. Rows and columns in a spreadsheet, like a patient's age or if they're a smoker. Easy. But unstructured data, like a cute picture of a puppy, absolute nightmare. To a computer, that picture is nothing but 3 massive tables of numbers from 0 to 255, representing red, green, and blue light intensity. Seeing the number 251 just means, hey, lots of blue light here. It doesn't tell the computer if that blue is the sky, a painted wall, or the ocean. The raw numbers just don't have any intrinsic meaning.
And this is exactly where deep learning completely changes the game. It solves this unstructured data problem by entirely removing the human bottleneck. In the past, PhD researchers would spend years manually programming features, like literally writing code to measure a bird's beak length from an image. Deep learning just skips all of that. It automatically learns its own representations straight from the raw pixels. It figures out how to extract patterns hierarchically on its own. So it starts with simple lines, combines those into curves, and eventually recognizes a whole face. Pretty wild, right?
Moving on to Section 2, Anatomy of a Neuron. Let's take a step back from the abstract and look at the fundamental mathematical engine making all this happen. Every neural network is built out of individual artificial neurons, also called perceptrons. And honestly, no matter how advanced the AI seems, a single neuron is basically just doing 3 very specific mathematical steps. Step 1, it takes incoming numbers and multiplies them by its weights, which is really just deciding how important each input is. Step 2, it adds a single number called a bias to shift the result. And step 3, it passes that final number through something called a nonlinear activation function.
Let's zoom in on that last step for a second, because the activation function is crucial. It acts as a mathematical gate that introduces nonlinearity. Without it, the whole model just acts like one rigid straight line. And if you've ever tried to draw a perfectly straight line through a chaotic, messy scatterplot of real-world data, you know it's completely useless. The real world is messy. It's nonlinear. The activation function lets the neural network actually bend and flex so it can approximate incredibly complex data.
Now, the absolute hero of modern deep learning, hidden layers, is this specific activation function called ReLU, or rectified linear unit. And it's beautifully simple. If the incoming number is positive, ReLU passes it along exactly as is. If the number is negative, it just outputs a flat 0. That's literally it. It's incredibly fast and efficient to compute, but it introduces the exact nonlinearity the network needs to tackle massive problems.
Okay, Section 3, Building a Deep Network. So how do we go from one neuron to a full brain? You take that single artificial neuron we just talked about, and you stack it alongside a bunch of others to create a layer. Then you stack multiple layers one after another. What you've got now is a feed-forward neural network. You have an input layer where your raw data comes in, you've got multiple stacked hidden layers sandwiched in the middle, and finally an output layer that spits out the prediction.
When we say deep learning, we're literally just talking about having many of these hidden layers. And it's deep inside those hidden layers where all that automatic feature extraction magic actually happens.
Let's ground this with a quick practical example. Imagine we're trying to predict a student's chances of passing a class. Our inputs are the number of lectures they attended and the hours they spent on the final project. Those numbers flow right into the input layer, travel through the hidden layers, which are all heavily connected with those weights and biases we mentioned, and finally the output layer delivers a single probability score, say an 85% chance of passing.
Which brings us to Section 4, how machines actually learn.
We know the structure now, but how does this thing actually get smart? I mean, the inputs and outputs are fixed based on whatever problem you're solving. But what about those millions of weights and biases hidden inside? The ones doing all the multiplying and adding? We humans don't set those, the machine does. So how exactly does the network figure out the perfect configuration of millions of weights, entirely on its own?
Well, to learn anything, the network first has to realize when it's made a mistake. Enter the loss function. This is just a mathematical way of measuring how far off the network's guess is from reality, the ground truth. If the network predicts our student is going to fail, but the historical data shows that student totally crushed the class, the network gets penalized. So the entire goal of the learning process, just minimize that loss.
And to minimize that loss, it uses a brilliant algorithm called gradient descent. Imagine you're a hiker, dropped onto a foggy mountain, and your goal is to find the lowest possible valley, because the lowest valley represents the absolute lowest possible error. You start at a totally random point, which translates to the network starting with random weights. You feel the slope of the ground under your boots. That's computing the gradient. Then you take a small step downhill. The size of that step? That's what we call the learning rate. You just repeat this process millions of times until you finally hit the bottom of the valley.
Okay, but calculating the slope of a mountain for a network that has millions of dimensions or weights, that's serious heavy lifting. And that lifting is done by an algorithm called backpropagation. It essentially uses the chain rule from calculus to work backward. It starts at the output layer, moves all the way back through the hidden layers to the input, and figures out exactly how much to tweak every single weight so it gets a better, more accurate result the next time around.
Now, if you tried to do this calculation over your entire massive data set all at once, what's called full gradient descent, it would be agonizingly slow. So instead, modern deep learning relies on mini-batch stochastic gradient descent. It grabs a small, random chunk of data, maybe just 32 examples, calculates a slightly noisy gradient, and takes a quick step. It is remarkably fast, highly stable, and it plays perfectly with the parallel processing power of modern computer hardware.
All right, Section 5, the overfitting trap.
Here's the catch. Just learning the training data isn't enough. The AI has to genuinely understand the patterns. There's a huge danger during training that the model basically becomes a giant memorization machine. If you have a massive network but a small data set, the network might literally just memorize the exact answers to the training set. We call this overfitting. And the second you show it brand new, unseen data in the real world, it crashes and burns. What we're actually aiming for is generalization, where the model learns the flexible, underlying concept so it can handle surprises it's never seen before.
So how do we force the network to generalize? Researchers use a brilliantly counterintuitive technique called dropout. During the training phase, you randomly turn off a chunk of the neurons, say 50% of them, for each pass. This forces the network so it can't just rely on one single, rigid neural pathway to get the answer. It essentially has to learn multiple, robust ways to arrive at the exact same conclusion.
Honestly, almost everything we've talked about today, the neurons, backpropagation, gradient descent, these mathematical concepts have actually been around for decades. So why is AI exploding right now? Well, it's the perfect storm of three massive pillars: an exponential explosion of global data, the insane parallel computing power of modern GPUs, and the democratization of open-source toolboxes that let pretty much anyone build these networks. This trifecta is the true engine behind the deep learning boom.
We kicked off this explainer talking about Polanyi's paradox, the idea that humans know way more than we can explicitly code or explain. By automatically learning its own representation straight from raw data, deep learning totally bypasses our human limitations. Which really leaves us with one fascinating question to ponder. As these neural networks map out increasingly complex layers of reality, what hidden fundamental truths are they going to uncover next that our human intuition has entirely missed? Thanks so much for joining me on this explainer, and I'll catch you next time.